next test from this section and the next section that we're going to cover, and a couple of them for the final. So we are going to talk about the relative maximum and the relative minimum that we started the other day. Okay, so in this chapter, basically optimization problem is the target. Okay, so we are going to find where the function can have a maximum or can have a minimum. Okay, we gave you the basic definition of these quantities the other day, so we are going to do it. Okay, let me know if you have any question when you go through this a couple of theorems that we discussed today. Okay, that's going to be 3.1 as we started the other day. So we are going to focusing on, again, a relative. Okay, relative and absolute extrema of functions. So we get some observation from some examples that we did the other day. So the observation was this maximum and the minimum of the function are going to be happening at two places. So if the function is going to be a smooth and nice one, this is going to be the one. So the maximum and the minimum, this is going to be the maximum, and this is going to be the minimum. And we observe that at these points, the tangent line is going to be horizontal. You see, and you know that the tangent line is going to be horizontal if the slope is 0. The slope, of course, is the derivative. So in this case, you just let f prime of x equal to the 0, and you are going to get your maximum and the minimum. So this is going to be the case that it's happened when you have horizontal, okay, horizontal tangent lines. So that's the first case that you have to consider, the places that you want to find the maximum minimum. But there are some other continuous function, you know, that we are going to have a continuous function with a sharp corner, like the Weierstrass functions, or like the absolute value function. Look at this function. So the case 2 is like the absolute value function. So the absolute value function, if you graph it, you see if you graph it, that this is going to be the graph of your function. The graph of the absolute value function. You see this is the function. So at this point, you are going to get the minimum. So 0 is the minimum value of this function. But as you can see, you cannot have a horizontal tangent line. In fact, the derivative of the function does not exist at this point because it's a sharp corner. So we refer to this as you are going to have a kind of a tangent line, but your tangent line is going to be vertical. And you know that if the line is going to be vertical, the derivative of that line does not exist. Sorry, the slope of the line, we say it's undefined, and of course the derivative does not exist. So in this case, this is going to be the case that f prime of x in general, that's f prime of 0, 0. Okay, in this case, I just explained that f prime of 0 is going to be undefined. It's going to be undefined, and you are going to get a vertical line. You see, you get the vertical, horizontal line, vertical tangent line, tangent line. So that will tell us that there are two possibilities when we get the maximum and the minimum. So this will tell you that if you see, if the conclusion is going to be that if you know the function at some point, if f of c, if you like, if f of c is going to be a kind of a relative, we stay with the relative extrema. Okay, relative extrema, then you have two possibilities. So the possibilities are going to be that f prime of c is equal to the 0, as in this case, or f prime of c does not exist. Okay, does not exist. So as you can see, if this is going to be 0, you get horizontal tangent line. If this is going to be the case, so f prime of c does not exist. You may see, so this is not a coincidence. It's not a coincidence that you get these cases, but this is your observation. But this was observed by great mathematician Fermat for the first time, and this would make one of the basic theorem of calculus. Okay, so we make it official. And the observation is a great theorem. So that would be our theorem. This theorem would provide the roadmap. So exactly what we did over here, but we got to be a little bit more precise. So this is going to be called, of course, Fermat got quite a lot of formulas. You know that he did mathematics, he was a lawyer, and he did mathematics as his habit. He is one of the people who just discovered probability and quite a lot, you know, more than 500, 600, 700 different theorems. Okay. But his famous works are on number theories, but you got some nice theorem in calculus, and this is one of them. So exactly what we have over here, but we got to be precise if you want to prove it. Say, suppose you have a function, but your function must be, of course, continuous. A function f is going to be continuous. That's a condition that you should have. Continuous on a closed interval of a comma b, and c is a number inside. Okay, is going to be inside this interval, inside the interval. Okay, inside we mean it cannot be. Okay, it cannot be at the endpoints. You discussed. I think you were one of you asked the other day. For that, I explained it that because if you're going to be at A and the B, then differentiability is going to be kind of one-sided one, and it cannot happen. Okay, so this theorem only true when we talk about the inside points. So suppose f is a continuous on this, c is going to be a number inside the interval a and b, such that the function at this number, okay, such that the value of this value of these points, or the value of the function at this point, such that f of c is going to be a relative extremum, means a relative maximum or a relative minimum. So such that f of c is a relative, okay, relative extremum, either a maximum or a minimum. If this is going to be the case, then the one that we talk about it, there are two possibilities. Then we have two cases. F prime of c is equal to the 0, or f prime of z does not 0. Okay, it does not exist. Exactly the case that we talk about it. Okay, so in order to know, some people remember that when they see it visually, if you like, you know, they have this type of interpretation. So we are going to mention, oh, what does it mean from geometry point of view? There you are, from geometry, tangent line problem. So that's it. Geometrically, that's it. If f is differentiable, if it's going to be differentiable, you have only this case. If it's going to be differentiable at x equal to the c, because if the derivative does not exist, okay, then there is a horizontal tangent there. There is a horizontal, okay, there is going to be a horizontal tangent line to the graph. Tangent line to the graph of the function, to the graph, okay, graph of y equal to the f of x, of course, at that point, at x equal to the c. That gets done, you know, when we do the function of several variables. Again, we use this one. Okay, so that's going to be geometry. You know, it's a great theorem. I can give you a short proof, one line really, so that you can see. It's not bad to see. We are not going to ask you to prove it. It's a great theorem. So you see the geometry, you see the abstract. So you may say, oh, how am I going to prove it? Very nice, easy. Okay, so let's have a look at the proof. So that's it. I can prove it for you in one line. So how am I going to prove it? Okay, you see, you want to prove that it's a extremum. So take one. Which one do you like? Maximum or the minimum? I can do both of them for you. Okay, so pick one of them. So for example, you may say, okay, suppose I like maximum. So we have all this information that we talk about it. So suppose C is inside A and B. Remember, no, you can't do it for the end point of the interval. It must be inside. Suppose C is inside A and B such that f of C, doesn't matter, max and the mean, I can do both of them for you. I do the maximum, is a relative maximum, okay, relative maximum of f. Remember relative maximum, what does it mean? This means it's a great value of the function, but only in my neighborhood. Okay, so this means the meaning is, so what's the definition? Definition is going to be, is a big value of the function. So this means f of C is going to be greater than f of x or greater than equal to, doesn't matter. But for a while means for all x near C, a little bit to the right, a little bit to the left. Okay, so this is what you give me. So what I want to prove that, I want to prove that f prime is 0. Of course, if f prime of C does not exist, I'm done. So I'm not going to care about that one. I say, oh, if I know that if f prime of C, okay, does not exist, then we are done. We proved it. We are done. Because that's one part of the theorem. Okay, so we are going to assume that f prime of C does exist and we prove that it's 0. So we assume, okay, assume that f prime of C exists. Okay, then we prove that it's going to be equal to 0. Okay, so required to prove that. So the target is, so the target, okay, the target is to prove that f prime of C is equal to 0. So that's going to be our target, okay? So I'm going to prove it. Remember definition of f prime of C? What's the definition of f prime of C? There you are, definition of f prime of C. F prime of C is equal to, I use the slope form of the definition of the, secant form, secant line. F of x minus f of C over x minus C, x goes to C. That's the definition that you have. Remember, I want to prove that f prime of C is equal to 0. And I know that, you see, I know that f of C is greater than f of x. So this means the difference between f of x and f of C is always a negative number at the top. So what I'm going to do it, because it's a little bit, near C. Near C means going to the right, to the left. You know that when the limit does exist, then the right limit and the left limits are going to be the same thing. Okay, so I go to the next page and continue. Any question? So I want to prove that the f prime of C is positive. Sorry, it's equal to the 0. So according to the definition of the limit, this means, okay, this means this is what you have. You have f prime of C is equal to the right and the left limit, the limit of f of x minus f of C, x minus C, x goes to C negative, is equal to the limit of f of x minus f of C, x minus C, x goes to C positive. Look at this one. So I take him one by one. Take this one. So if you take this one, you have f prime of C equal to the limit of x minus x goes to C negative. The top would be f of x minus f of C. The bottom one would be x minus C. Now I would like you to check the sign of the top and the bottom. Sign of the top and the bottom. What do you know about the top? Remember, f of C is the maximum. You see, look at this one, note that. Remember, f of C was the maximum. Maximum means what? F of C is greater than f of x. If you move it to the other side, that give you f of x minus f of c is a negative number. That's the top. How about bottom? The bottom one also. X goes to c negative. What does it mean? This means, remember, x is less than c. X is less than c means what? X minus c is less than 0. You see, look at this one. Negative the sign. Negative, negative. So what is going to be the sign of this? You see, so this means f prime of c, which is equal to the limit of f of x minus f of c, x minus c, x goes to c negative. You see, the top is a negative number. The bottom one is negative. Negative, negative would be positive. So you are taking the limit of a positive number. So this limit can be only positive. It's going to be greater than equal to the 0. It may be 0, but it's always positive. You see, that's the case 1. Remember, I want to prove that f prime of c is equal to the 0. Any question? That's fun to know, really. This is a great theorem from the history point of view. Okay, so this is what I check this one. Now, if you take the other one, what are we going to get if you get the other one? Similarly, you see, if you take the other one, f prime of c is the limit of f of x minus f of c, x minus c, x goes to c positive this time. You see, remember the top is already negative. But the bottom one, when it's go to c positive, remember it's from the right. When it's from the right, this means, you see, this means x is greater than c. This means this is positive this time. Negative positive would be negative. So it's a less than, but it may be 0, less than equal to the 0. So this would give you what? Give you f prime of c is less than equal to the 0. You see? So what do you have? So we have the case that f prime of c is greater than equal to the 0, and f prime of c is less than equal to the 0. What's the conclusion of this one? You want a number to be greater than equal to the 0, and at the same time to be less than equal to the 0. What's possibility for this one? For this number, f prime of c? Any suggestion? You want f prime of c to be bigger than equal to the 0, and at the same time to be less than equal to the 0. So what is going to be the possibility? Any suggestion? What can you conclude about f prime of c? You want it to be great. You see, if you consider any number, what are going to be the possibility for the number? Number can be positive, number can be negative, and number can be 0. Your number, you want your number to be greater than equal to the 0 and less than equal to the 0. So you cannot have it at the same time to be positive and the negative. So the only case that you can have is that f prime should be 0. That's it. Great theorem. You see, with the help of the right and the left limit, I proved that if you get a maximum f prime of c, the first case would be greater than equal to the 0. The second case would be less than equal to the 0. So we would like to have a number that satisfies these two conditions at the same time. The only number is 0 because you have equality sign here and equality sign here. Okay, so that's going to be the way we prove it, the Fermat theorem. Again, I prove it for you so that you can see how easy it is to prove. That was geometry, and you get these numbers. So we prove that if f of c is a relative maximum, f prime of c would be 0. Similarly, you can prove that just to finish it. Similarly, if f of c is going to be a relative minimum, then f prime of c would be equal to the zero. Okay, so that's a proof of the Fermat theorem, because this is foundation of your job right through this section and in calculus. So it's not bad to see it and see how easy it is, to prove the theorem. If you like proofs, but if you don't like it, just going back to the theorem and we continue. Any question? So that's for the proof lovers, if you like. But so we're going back to see what we did prove. You see, that's it. So we proved whatever we saw here. You see something, you prove it. So we prove that if f of c is a relative maximum or is a relative minimum, it should happen at two places: horizontal tangent line and the vertical tangent line, if you like. But the question is going to be, so remember, you are looking, but the Fermat theorem is a nice one, but the Fermat theorem gives you the property of it. It doesn't say anything for finding that the maximum and the minimum. This said, if this is, this means some people think that if they find the derivative of the function and let it equal to 0, 100%, they get the maximum and the minimum, which is not correct. Okay, so the difficulty about the theorem is this is just a road plan. This is a possibility. So you have to find this and then check. We are going to have some theorem to check it. So we give you a warning, then we give you an example. So the warning is going to be the converse of this theorem. Most of the people, they make a mistake when they use it. The converse of this theorem is not true, which means if you have a function, you differentiate it, you let it equal to the 0, and you find the solution of this equation or this one. It doesn't mean automatically that f of c is going to be maximum and the minimum. You need more to investigate. So we make this remark, and then of course we give you examples. Okay, so we spend a little bit more time on this because this is very important result. I would like you to make sure you see it. Okay, and of course, if you want to take calculus 3, that would be a motivation that we use over there in order to find it. We prove here, but over there we use it as a definition. So give you a big remark, and then we go to the example. What's this remark? The remark is convince you, because there is a theorem that you have to use, and some people say, oh, I don't need that theorem. So we just give you this remark. The converse is not true. So this means the converse of the Fermat theorem, of the theorem, the above theorem, the theorem, okay, is not true. Maybe true sometimes, most of the time. It's not true in general, not true in general. What does it mean? This means I can give you a function. When you say it's not true in mathematics, you should give us a example. We call it a counter example. So I can give you, there is a function. Always in this course and in calculus 3, we bring this example, a similar one. There is a function f and a number c, such that f prime of c is equal to the 0. You see, is equal to the 0, but f of c is not a maximum and the minimum. Is not a relative, okay, extrema. Relative extrema. Okay, so this means you have to do something else for us. So you need to know this example. It's a very famous example. It's kind of unique example. Okay, and the famous function that would reject the converse of the Fermat theorem is x cubed. Okay, so suppose f of x is equal to the x cube. In your book, they give x minus 1 all cube. In some books, x plus 2 cube. But it must be cube function. Okay, cube function. Look at this. So what we'd like to do is we'd like to say that, oh, if you differentiate it, okay, look at this one. If you differentiate it, then find the derivative of the function. You see, f prime of x would be what? 3x squared. That's derivative. Let it equal to the 0. You did it on the quiz, remember? You find derivative, let it equal to 0 to find the horizontal tangent line. So this would give you what? This gives you x equal to the 0. So this x equal to 0 is like the c. So what we did over here, okay, so we have the case that f prime of c is equal to the 0, you see? So c is 0. So the question is f of c, you see the question is f of 0 a relative maximum or a relative minimum. Just look at the graph. So look at this graph. This is the graph of the x cubed. You see, this is the graph of the x cubed. And this is 0. You see, this is 0. So, and this is f of 0. You see, f of 0 is equal to the 0. F of 0 is equal to the 0. You see, if you say that, remember, if you claim that this is a maximum means this must be maximum value of the function. Is it the maximum value of the function, relative maximum? No, because there are lots of more, you see, you have many more formulas or points above it. You see, so these values are all above f of 0. So you cannot say that f of 0 is the maximum value of the function. Is it a minimum? Minimum is, this is the lowest value of the function? No. Look at these points. You see these points, point. So we get lots of values below it. So f of 0 cannot be a maximum, just the spot or value of the function, and they are all greater than f of 0. F of 0 cannot be negative because all these purple one values are below the f of 0. So you have a case that, you see, so you have a case that this is it. So the case is that f prime of 0 is 0, but f of 0 equal to the 0 is not, okay, is not a relative extrema. Okay, so the converse of the Fermat theorem is not going to be true. So what does it tell you? This will tell you that the result of the Fermat theorem, those f prime of c equal to 0 and f prime of c does not exist, they are the candidate for the maximum and the minimum. So this means first you have to find them. Then you have to investigate it. Those investigation means we need more theorems. And those theorems are going to be coming. We're going to use two different, we call them tests. One of them is called first derivative test. The other one is called second derivative test. So we investigated whether they are going to be a maximum and a minimum. But since they are VIP's numbers, okay, good numbers, our candidates, we are going to give them a name. The name is critical values. In some books, they go with the critical numbers. But I usually go critical, values, but it doesn't matter, number or values. Okay, so we are going to make them candidates and then we investigate it when we get the maximum and the minimum. Okay, any question? So the roadmap, the possibilities are, as I talk about it, two places, there you are. the place that you get the horizontal tangent line, so f prime of x equal to 0, and the place that f prime of c, c does not exist. Vertical tangent line, horizontal tangent line. These places are going to be called numbers, the values are going to be called critical values, and then we investigated whether we get these, and we get any maximum or minimum at this point. So everything I did so far was a motivation for these definitions. Critical numbers or critical values, whichever you like. You will go with the second one, but it doesn't matter which one do you like. You can use it. Okay, I call them 50% because from now on, any problem that you are going to solve for us, you have to use this. And that would form 50% of your grade, of your point on each of the problems. Because without this, you can't do anything, okay? And we give you all the possibilities and you practice and you'll be fine. So what is these numbers? The one that we talk about, the result of the Fermat theorem. If a function f is defined on the domain D, you have to find the domain first. On the domain D. Okay, this is your function. Okay, there you are. A number. C. Okay, in the domain D. It must be in the domain. It's called, okay, this number is called a critical number. A critical number. Okay, or critical value, or a critical, whichever you like. Depends on the book that you're going to use. Okay, critical number or critical value for f or of f, for the function f, for the function f, if this number is coming from two different sources. The source are going to be where we get the horizontal tangent line, f prime of c equal to 0, or the source that you're going to get vertical tangent line, f prime of c does not exist. There you are. So in order to find them, you have to check these two cases. If the function is fully differentiable, you ignore this. You just let f prime equal to 0. But if the function are not going to be fully differentiable, so you have to consider this one. This will happen mostly for the, okay, most of the time for the radical functions for the time being. Okay, so this is going to be the definition. This is a roadmap. The possibilities. So we have to check the possibility first. Any question? So I explained it. I'm not going to explain it again. Geometry means this is the where you get the horizontal tangent line. Okay, where we get the horizontal tangent line. This is it. And this is where we get the sharp corner. At the sharp corner, over here, f prime of c is equal to 0. Over here, f prime of c does not exist. So two places to look for it. Okay, now your job is to find them. There are 7 types of functions because the way we are going to edition of your book, 2 of those types would be left out for the time being. And we come back to it when we get to the final part of the course, and they are natural log and exponential functions, which are very important. But I just stay with the book, the Larson book, the calculus for, okay, by Larson. So we talk about it later. But otherwise, 5 different cases, and this is going to be your road, your tools for the rest of the course. Make sure you know it. We give you all the 5s on your next test. Okay, so there you are. Find all critical. Okay, I'll go with the values, but we can go with the numbers, doesn't matter. Find all critical values of the function. So these are your tool. Just get to know them, and anything else we talk about it in this chapter. We go with this one first. Okay, so there you are. Are you ready? And this is the way you write it down on the test. Make sure you follow my instruction. Part 1. The first case, of course, the most popular one, polynomials. There are going to be quite a lot of polynomials. So get to know them. 2x cubed minus 3x squared and minus 36x plus 14. That is, of course, we know that it's a polynomial function, combination of powers of x. Okay, are you ready? You want to find the critical values. Step 1, the domain. You must make sure that the points that you pick are going to be in the domain of your function. If you don't give us a domain, you miss the point, okay? So solution, domain first. You know that it's a polynomial function. Domain is going to be, okay? Just remind yourself, just write down, just give you, write down all your information. F is a polynomial. Okay, it's going to be a polynomial function. And so the domain of this function is going to be all real numbers, R. That's the step 1. Remember, because your critical numbers must be in the domain. So that's the first condition. Question? This function is nicely differentiable. So differentiate greater or equal to 0. So what you have to do is solve this equation. F prime of x equal to 0. You remember, you did it before, because that's why I just wanted to practice, because this is where you find the horizontal tangent line. So repeat it. F prime, carefully differentiate. You know that the power rule, 6x squared minus 6x minus 36. That's your F prime. You highlight it because you want to use it. Let it equal to the 0. Carefully, okay, solve this equation. Most of the time, factoring would do it for you. You may have to use quadratic formula. Don't be shy. Make sure to remember the quadratic formula, especially for the problems in your book. Okay, I just remind you the formula. This is it. X equal to the negative b plus or minus. Okay, there you are. This is the way I write it down. Delta over 2a. And then delta is b squared minus 4ac. You're going to see it, use it, so make sure you remember it. But we don't need it for this. We try to factor out the 6 first, which is possible. Pull out the 6. So the leftover, x squared minus x minus 6 equal to the 0. Okay, you factor inside. So that's going to be 6 times. You need 2 numbers, okay, with the product of 6 and a difference of 1. Of course, the number is going to be x minus 3 and x plus 2 equal to the 0. Factors equal to the 0. 6 is never 0. Some of you missed it on the test. 6 is never 0. So x minus 3 equal to the 0. That gives you x equal to 3. One solution. X plus 2 equal to the 0. That gives you x equal to the negative 2. That's it. Critical values. I'll go with the CV. Critical values are going to be negative 2 and 3. And you're done. For the time being, this is the only job that you're going to have. Of course, when we get to the maximum minimum, that would be first a step that we take. Any question? That's the first group. Get to know them. Okay, polynomials. The most popular one or the most frequent one. Domain first. Since they are differentiable, you don't have to worry about the vertical tangent lines, horizontal. So take the derivative equal to 0 and solve it. So that gives you, there is no possibility for the second part. F prime of c does not exist because this function is differentiable. So that's the case 1. Question? Case 2. Rational function, of course, that's case 2. Case 2. Rational function. We go with this one first. They are very popular. So f of x equal to x over x squared plus 60. Rational function. Domain first. You know that you focus on the denominator because this is defined everywhere unless denominator would be 0. Denominator is x squared plus 16. You know that x squared plus 16 is never factorable. We don't use complex numbers. So since the denominator is never factorable, so you never have 0. So this means this function is defined forever, okay? So this is how you define it for yourself or explain it. You may say that x squared, this is again, just for your information. X squared plus 16 is not factorable. Okay, it's not going to be factorable, which means it's never 0. And so it's never 0. So this means the domain of your function is all real numbers. Nice. Nothing to worry about. Okay, that's a domain. You have to find the domain first. Next, this function is nicely differentiable. So we're just looking for the horizontal tangent line. So we have to solve f prime of x equal to the 0. Quotient rule only. Derivative of the top times bottom. Okay, so this is the one that you're going to use, top, bottom. You differentiate. Derivative of the top, t prime, times bottom, minus derivative of the bottom, b prime, times top, divided by the bottom squared. Okay, carefully apply the quotient rule. Of course, anytime you use quotient rule, you know that you have to simplify it. Okay, are you ready? F prime of x equal to top, bottom, derivative of the top, derivative of x is 1. I write it down so you know what's going on. 1 times x squared plus 60 minus bottom top, derivative of the bottom, derivative of x squared 2x, derivative of 16, 0. So it's going to minus 2x times it by the top, divided by the bottom square, x squared plus 16, all squared. Stay on the top and simplify. So it's going to be equal to, that give you x squared plus 16 minus 2x squared, divided by x squared plus 16, all squared. Stay on the top, simplify. Combine the like terms. You combine the like terms on the top and you arrive at f prime of x equal to the top, negative x squared plus 16 divided by x squared plus 16 all squared. That's it. That's a derivative. Any question? You did it equal to the 0. You see, a fraction is going to be equal to the 0 only if the top is 0. Because 0 divided by 5 is 0, 0 divided by 6 is 0. So you want f prime to be 0, so that would imply that it would happen only if the top is 0, x squared plus 16 equal to the 0. Any question? Now you solve for x, different way to do it. You can factor it or you can move one of them to the other side. If you move the x squared to the other side, that gives you 16 equal to the x squared. And you take the square root and that gives you x equal to the positive negative 4. So you are going to have two critical values. The critical value is going to be negative 4 and positive 4. And you're done. Again, there is no chance for the second case. The second case is when f prime does not exist, because the domain of this function is all real numbers, and you have no other choice. It's not going to happen for the rational function. Always horizontal tangent lines are going to be, for this group, are going to be, okay, horizontal. And that's it. That's it, type 2. Any question? So the type with the rational function, you got to be careful. Some people, they miss the algebra here. Okay, it's derivative of the top down bottom, top, bottom, bottom tab. Carefully use parentheses. Sometimes you may have to use the FOIL method, okay, which is going to be nice. But you stay on the top, simplified. Fraction is 0 only if the top is 0. You see the fraction, because that 0 divided by number. You cannot have 0, 0. So it's only 0 on the top. So you let the top to be equal to 0 and you solve it and you get the result. Okay, any question? That's case 2. Case 3, very popular, and you already did it on your test. So you will see it again. I told you this type of problem is going to be repeated. What's case 3? Of course, trigonometric one. Like the one on the, okay, on your test. Some of you missed it. Check that because it's going to be coming in any test, any quiz. Okay, this problem would be repeated. Remember, I gave you 6 of these types. X plus or minus 2 sine, X plus or minus 2 cosine, and those 2 fractional one. So check them. They are coming in any test. I told you, we have to give you one question from the involving trigonometric functions in any quiz and test in calculus. So it doesn't matter, where you take this course or which book are going to use. They question you. So they give you one period. That's it. You need the unit chart. And you have it, the unit circle chart in any test. So there you are. The domain is already given to you. Domain is just the closed interval of 0 and 2 pi. And the function is nicely differentiable. So you're going to solve f prime of x equal to the 0 to get your critical, okay, to get your critical values. Carefully differentiate it. F prime f of x1 minus 2 times derivative of the sine, cosine. 2 times cosine x. Let it equal to the 0. 1 minus 2 cosine x equal to the 0. And you solve for the cosine, you know that. You move the negative. You need the 1 to the other side. And you arrive at the fact that the cosine x is equal to the 1/2. Cosine x equal to 1/2. So you go to the unit circle chart, you know that there are 2 possibilities and you give us 2 solutions. If you go to unit circle, okay, remember this is the cosine and this is going to be the sine. So this is cosine. So you want it to be positive. So one of them should be here and one of them must be here. And you check the chart. In the first quadrant, 1/2 is the cosine of the 60 degrees. Pi third, 60. Okay, and this is going to be, of course, 180 minus 60, which is, oh, I'm sorry, I missed it. Oh, I missed it. The cosine positive. Where is the cosine positive? Cosine is not going to be positive here. Okay, one of them is here and one of them is here. Okay, cosine is positive in the first quadrant, cosine, and cosine going, your chart you will see it. I just want to explain it. So your cosine is going to be positive in the first and the last. So this is 60 degrees. Okay, this is 60. So that is 300 minus 60, which is going to be 300 degrees, which is 5 pi third. 5 pi third. Again, the table is given to you, and then you can find it. So 2 numbers, x equal to the, okay, pi third, one solution, and x equal to the 5 pi third. It's important, to pick the correct one, because they are going to be the maximum, the minimum in future. So you have 2 critical values. The critical values are going to be pi third and the 5 pi third. Okay, so just practicing, just make sure this one, this one is right. So very important category to be given to you. Okay, so far so good. We cannot give you, or we are not going to give you now exponential function and the log function. We talk about it when we get to the next chapter, because I know we just stay with your textbook. So these are going to be ordinary one that you see so far. So in this case, there is going to be one VIP, and this is going to be the next one. Okay, the next one is the one that you got to be careful. Anytime you see a radical expression in your function, or the function is going to be a radical function, you got to be careful in this course, especially when you're dealing with this critical value, because whatever you want to do, you have to find these critical values. Okay, so the next group are going to be considered the VIPs of this group. Okay, and you will get it, in any test that they give you one. So pay attention to the number 4. So what's going to be number 4? Starting with this one to warm up, then we upgrade it. Let's check this. F of x equal to the cube root of x minus 9. That's a radical function. You have to find the domain of this function. Any suggestion? What's the domain of this function? Cube root of x minus 9. Any suggestion? Yes, we have one answer. Let's see. Okay, Geneva, yes, all real numbers. You're correct. Yes, you know that you have to look at the index of the radical. Index of the radical is odd. When the index of the radical is odd number, forget it. Look at inside. What type of function is this? X minus 9 is a polynomial function. So when it's a polynomial function, the domain is all real numbers. Okay, for the radical function, depends on the index. Remember, if the index is even, you are going to be in trouble because the inside must be greater than or equal to the 0. So it's very important to identify the domain carefully, okay? And it's important if you don't give it the domain of the radical function, you missed half of the problem. You will see it in a minute why the domain is such an important case here, okay? So I just remind you, solution, I need to find the domain, so I look at the index. So index of the radical, again, you don't have to explain if you can get it right. Index is 3, is odd. So I can have anything inside the radical, positive, negative numbers. And so, I don't have to worry about the domain. Domain is all real numbers. Any question? Now, you want to find the critical values. So remember, you have the two options. So the options are going to be target are going to be, you are going to solve this equation as you did for the other. But for the radical function, there is going to be another option. The other option is f prime of x, okay, does not exist. Remember horizontal tangent line or vertical one. In the case of the radical function, you will see in a minute, you may get to the situation that this f prime won't exist. So you have to consider two different, that's make it different from the other. Okay, so let's go with the derivative first to see what's going on. You want to differentiate it, of course, you have to remove the radical, you have to rewrite it, f prime of x is equal to the x minus 9, everything to a third. Then we want to differentiate it, of course, we have to use the chain rule. Okay, we have to use the chain rule because you have to consider this one to be u. Okay, and remind yourself that you have to differentiate u to the 1/3. And you know that u to third would be what? Would be 1/3. U to the 1/3 minus 1, which is a negative 2/3. Okay, times the u prime. So operate. So this is it. Your f prime of x is going to be equal to the power down 1/3 x minus 9 to the negative 2/3, 1 minus 3 times u prime. U prime derivative of the inside. Derivative of the inside is 1. So continue, these are monomials, you multiply together, and you have to simplify it. You see, rewrite it as a positive power here. So this is going to be f prime of x is equal to the 1 on the top. We get the 3 already, and then we bring x minus 9 to the 2/3 down the bottom. So this is going to be your f prime of x that you have to investigate. Any question? Now we're investigating these two cases that we have. For the case 1, we let f prime to be equal to 0. So check f prime of x equal to 0. So what would happen to this one? It's going to be a fraction, 1, 3 times x minus 9 to the 2/3 equal to 0. So a fraction would be 0 only if the top is 0. So this means the top must be 0. 1 equal to 0. 1 equal to 0 is impossible. So you didn't get anything from this one. Okay, so this means f prime of x cannot be equal to the 0 here. Some people, they stop here. They say, oh, this equation has no solution. You see, this equation, f prime of x, so, they say f prime of x equal to the 0 has no solution. And then they conclude that there is no critical value, which is not correct. Yes, there is. You cannot get any critical value from this group. But remember, we did have always two sources. The source at f prime of x equal to 0, that's one source. We check for all of them. But since you didn't get anything here, so you check to see if there is a possibility for the other one. Okay, so you are going to check this possibility. Are you going to get anything from this part? You don't have to check it for the others. Okay, you're just checking this one. So this means, can you find a value of x that make f prime of x does not exist? Let's go to the function here. Look at the f prime. This is f prime. Look at the domain of this function now, domain of the f prime. Anybody can guess what's going to be the domain of this function? You see, by the domain is a rational function. You know that the rational function is not defined if the denominator is 0. So this function is defined everywhere, except for the value of x that make denominator equal to 0. Can you give us a value of x that make this denominator equal to 0? For what value of x this denominator would be 0? Any suggestion? Give us a number, you plug a number for x that make this denominator.
9.
Excellent, it's 9, very good, yes, it's 9. So you have one. So now you have to explain, so, oh, note that f prime of 9, you see, f prime of 9 does not exist. Does not exist means at that 9, you are going to have a vertical tangent line. But you have to confirm that this 9 is in the domain of the function, of course. You know that f prime of 9 does not exist, and that's important because it may not be. If it's going to be outside of the domain, you cannot pick this number. So we say note that f prime of 9 does not exist, and x equal to the 9 is in the domain of the function. And that's exactly the definition of the critical value. Okay, is in the domain of the function. So that's it. X equal to the 9 is a critical value. It's of the second type that we talk about it. You cannot get it for the other method that we did, but for this one. Okay, x equal to the 9 is going to be a critical value. So from the horizontal tangent line, we didn't get any. But for the vertical line, because of the nature of this radical function, you get the fact that f prime of 9 does not exist. You have to explain that f prime, two possibilities, f prime of 9 does not exist, and it must be in the domain. Okay, so the conclusion is going to be, you are going to have only one critical value, and that critical value is going to be 9. That's going to be the picky point, if you like, the crucial point or crucial example that you are going to see from now on. So anytime it's a radical function, you have to check the second case, the possibilities. So when you get a prime equal to 0, that would be the possibility that you get a horizontal tangent line, but this radical function, because of this nature that you get some sharp corner, if you like, or some part that you're going to get a vertical tangent line. So you have to check it. You have to check it not to miss it. So no, some people, they say this function has no critical value. It's not correct. Of course, no critical value of the type 1. But for this specific number, you have the type 2 as well. Okay, I'm going to change it a little bit, but I would like to give a break now. Then you come back, we make this one a little bit more exciting. And that function is the one that we're going to use. Okay, and then we finish with the critical values. As I told you, you have to wait for those. The VIPs are 3 groups. And the group of the radical natural log function and the exponential function. We take those 2 later on, okay? But otherwise, we have, so we put them together. This is 7 things. Anything I talk about from now on, any theorems we prove, when you want to give an example, we bring one of these. Okay, one of these 4 types. Then you have to find the critical values first. So let's read it very carefully. Okay, let's have a break. We come back and then we give you one more of this group, and then we are ready. We have the critical values. What's going to be the next step? So at which point are going to get the maximum, and at which point are going to get the minimum? That's your job for the next, for the rest of this chapter. Okay, so see you in, that's 7:07. Okay, about 9:20, we continue. Okay, we're going to continue, give you a changing this one a little bit. Any question? So we focusing in this special case, the radical function. Okay, we determine the domain. And then the difference between this one and the other one is going to be the case that you may get some vertical tangent line. Okay, getting where the places that the tangent line does not exist, and you got to be careful. Now I'm going to change this one a little bit, and this is the function that we're going to use in future. Okay, I just change this x into the x squared. You see what's going to be, the new situation you're going to have. That would provide a kind of this is a special function that we're going to use it in a couple of places in future. So getting to know it, not bad. So that would be our last example of these critical values. And the function is, as I told you, just change it a little bit. There is one more group, which is a little bit algebra involved. I'm going to talk about that one later. So that would be cube root of x squared minus, okay, x squared minus 9. This is the one. So I change it to the x squared. Let's see what's going to be the difference. Now we start with the domain again. The index is odd, so the domain is going to be all real numbers. See, the domain is important. You saw it in the previous one that when you want to discuss that critical value at that last part, you need that domain. You need the domain all the time. So quickly, you say that the index of the radical 3 is odd. You say if it's going to be odd, you can have anything inside the radical you like. You check the inside function. The inside function is a polynomial, and the polynomials are defined everywhere. So the domain of this function is all real numbers. And so domain would be all real numbers. That's going to be a step one. So you check the possibilities. As we talk about it, you have to check two possibilities. Is there a place that f prime of x equal to the 0? That's first possibility. And is there a place that f prime of x does not exist? That is the second possibility for these functions. So to differentiate it, we have to rewrite it. So we rewrite it f of x as x squared minus 9 to a third. Okay, and we want to differentiate it, remind ourselves that we have to use, chain rule. So derivative of u to the 1/3 is going to be 1/3 u to the negative 2/3 times u prime. Okay, now we're going to operate. It's going to be f prime of x. So we bring the 1/3 down. So that gives a 1/3 x squared minus 9 to the 1 minus 3 negative 2/3. Of course, times u prime. This time the u prime is 2x. That's the difference between this problem and the other one. So we have to rewrite it, get rid of this negative power. So it's going to be a prime of, just put the monomials together. It's a 2x and the 1/3, put them together. So it's going to be 1 times 2x, which is going to be 2x over 3. Okay, that gives you x squared minus 9, everything to the negative 2/3. Okay, so rewrite as a fraction. It's going to be a prime of x equal to, we get a fraction bar. On the top, we put the x squared minus 9. Okay, x squared minus 9, everything to the 2/3. Okay, 2/3 and divided by, sorry, the leftover on the top is going to be 2x. Oh, I'm sorry, I have to rewrite it. I made a mistake. So f prime of x is going to be equal to, we get a fraction bar. Everything with the positive power on the top, we get 2x on the top. And down the bottom, you already got the 3. So you bring x squared minus 9 to the 2/3 down the denominator. This is going to be our f prime. Okay, I highlight it because it's important. I'm going to use it. Any question? Now check the possibilities. This one first. Let f prime equal to the 0, f prime of x equal to the 0. So it's a fraction. It's going to be 2x over 3 times x squared minus 9 to the 2/3 equal to the 0. It's a fraction. A fraction is 0 if the top is 0. So that would imply that the top equal to the 0. You see in this time 2x equal to the 0, you solve for x, that give you x equal to the 0. We get one solution. So this is going to be one of your critical values so far. Okay, so far x equal to the 0 is a critical value. So this is where you get from the first scope, first conditions here. So now you have to check to see if there is any possibility for the second case. Is there a place that f prime of x does not exist? Yes. Investigate it. You see again, this is f prime of x. F prime of x does not exist if the denominator is 0. So check to see for what value or values of x denominator would be 0. Any suggestion? For what value of x denominator would be 0? Any suggestion? Numbers? Check the numbers. I have one. Okay, you know what? It's right. X equal to 3. Any other suggestion? There is one more. Any number that you plug in for x?
-3.
Excellent, -3. So it's going to be positive -3 this time. Okay, that's the difference between, okay, the first case and the second case. In the previous case that I gave you, it was only x minus 3. In this case, we have x squared minus 9. So there are two places that the denominator are going to be 0. And you know that with the denominator is 0, then the derivative does not exist. So this means you get a sharp corner at those places. So now you have to explain it. You explain the fact that, this is just for your information. To find it, you let x squared minus 9 equal to the 0. So that gives you x equal to the positive -3 in this case. And you have to explain it. Explanation is going to be the fact that this is it. You say, oh, f prime of at 3 or -3, positive -3. All of them do not exist. That's it. And you have to emphasize that they are in the domain. Otherwise, you can't do it. And x equal to the positive -3 are in the domain of the function. Remember, the domain of the function is all real numbers. So the derivative does not exist, and they are in the domain of the function. So this means these are those sharp corners that we talk about it. Vertical tangent lines. So we get 2 extra, okay? So we get the fact that x equal to the positive -3 are also critical values. So we accept it on the test if you make it brief, but you have to explain this part for us. So what's going to be the conclusion? The conclusion is the fact that your critical values, you get 3. You get 1, 0 when you put the horizontal tangent line, the top 0, and you get a positive -3 when we get the bottom one. So you have 3, -3, 0, and positive 3. And that would be very important for us. In future, you will see that at -3 and positive 3, we get the minimum value, and x equal to 0, we get the maximum value of this function. So if you miss positive -3, you miss the minimum of the function, okay? So that would be very, very important problem for us. Any question? So only be careful about, these radical functions, okay? The fun part really is to be able to take care of this. And there is one more group that the radicals are going to be mixed, okay? And we need a little bit of algebra. I give you that one later on so that you show you how you get it, in the case of the more action that is needed. Okay, so that is our first action. Any question? Read it carefully. This is going to be your tool. Okay, these are the candidates. We are going to see them all over and over and over. These are the candidates that they are all satisfied. You see, they are all satisfied the Fermat theorem. You see, we are just checking these two cases. So there is a possibility that you may get the max and the mean on this, but there's no guarantee. We may not, but at least we know where we're looking for it. Okay, where to look for it. Okay, now what's going to be next step? Next step is getting back to our problem. So what was our problem? The problem really was finding the maximum and the minimum. So we just find the X values. So how are we going to find those maximum and the minimum? Now, at this level, remember we did have two types of maximum and the minimum: local, okay, relative, and absolute. Absolute value of the absolute maximum is the largest value of the function. Absolute minimum is the minimum value of the function, okay? But the relative one, we get it in the neighborhood of your place, okay? So what we can do at this level is quickly, we can solve the problem of the absolute max and absolute min. So we do this one first, and for the relative, we have more work to do. So at this level, let's take care of that problem first and make sure you know the difference between these two that we talk about it. So we check this one. So this is going to be our next second topics that you're going to have. We give you one of these on the next test, and of course on the final exam. Okay, so we are still in that section. So we are going to find locating, finding, okay, locating, absolute extrema, absolute. Mean the largest or the smallest. Locating absolute extrema, absolute extrema of functions. But we can only do it on closed intervals. Okay, find the absolute extreme of the functions on the closed intervals, on the closed, okay, intervals. You may say, what will happen if the interval is not closed? The answer is wait for it. But this theorem is guaranteed, okay, that you're going to get the absolute maximum. It's a great theorem. Again, we use it in calculus 2 for the function of several variables, okay? Exactly the same format. Of course, we change it a little bit. This theorem was proved by Agustin Cauchy, okay? He's a great, French mathematician. I talked about it before. We just polish the definition of the, okay, polish everything in calculus, really. If you are going to be a math major, calculus is a part of branch of mathematics that we call it mathematical analysis. And Cauchy is referred to him as the prince of analysis. Okay, and this theorem is one of his main theorems or results. Okay, they have to take care of to us. No test, nothing is needed. So what is this great theorem? Theorem, get to know these names. Okay, just check it on the internet to see the story about them. We refer to this theorem as Cauchy or Cauchy. Some people, they say it's a French name. Cauchy or Cauchy. Agustin Cauchy. You want to check it on the internet, you'll see him. That's it. What is this theorem? This theorem basically tell you that if your function, if you have a continuous function on closed interval, if you have a continuous function on a closed interval, there is a guarantee that you are going to get absolute maximum and absolute minimum. That's it. Cauchy theorem on a closed interval. Okay, so this is it. If a function f is continuous, must be continuous function, is continuous on the closed interval, let's say a comma b, it must be interval, must be closed for this theorem. Then there is a guarantee that you get one maximum, one minimum. Then f has, okay, an absolute and absolute minimum and an absolute or one absolute maximum in this interval. So there is a guarantee that you find a number C such that f of C is the largest value of the function, and you find a number like D such that f of D is going to be the smallest value of the function. That's the idea of this, okay, of this theorem. No test is needed. Okay. No, you cannot have a multiple absolute maximum and absolute minimum. You see, when we say absolute maximum, it's like a minimum wage. When we say minimum wage is what? Minimum wage is going to be $20. The minimum is 20, but how many people can get that $20? Many, 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 many. So you can have multiple points, but you cannot have multiple values, okay? Because when you say the maximum is the largest, so the value is unique, but you may get it at different places. Okay, make sure you know the difference. When you talk about the absolute max, absolute mean, we talk about the largest, and this is the range of the function. You see the range of the function. The range would be between, between 0 and 25. So the 0 is the minimum, 25 is the maximum. That's why we call it absolute. Okay, so this is going to be only one. You may have multiple points, but not multiple values. Okay, that's it. Any question? And now, it's a great theorem. It can be proved, so I'm not going to prove this one. But the question is going to be, okay, so what is the conclusion? The conclusion is this theorem would give you a news only. It says there is, but how are we going to find it practically? Okay, how are we going to find it practically? So the question is going to be where they are coming from. We know the candidates, remember? The candidates are critical values that we already talked about it. So the candidates are critical values. So what we have to do is we have to find the critical values. Then since we are looking for the largest and the smallest value, we find the value of the function at those critical values. And since this function is defined on closed interval, you may get this maximum and the minimum at the end point. So you find the value of the function at the critical points, those C that we got, and we find f of A and f of B. We compare them together because those are the possibilities. The largest value is the absolute maximum. The smallest value is the absolute minimum. So this is just the news. How we're going to do it in action? Okay, in practice, oh, okay, there you are. This is the instruction. In order to find it, the absolute, I just put the D, that it's going to be 1. The absolute extrema. This is your job. Step 1, candidate, maximum and the minimum, we know that. Those are critical values. Find all critical values of F. You know where are you going to find them? You are going to find them in 2 places when the F prime x equal to 0 or, okay, so you check for yourself. You check some source are going to be coming here and some source are coming from here. F prime of x does not exist. So this is where you find the critical values. Okay, step 2. Some of these critical values may not be in your interval. You ignore them because your function is restricted to this interval. So if a critical value is inside your interval, inside your domain, find the value of the function. Okay, so this part what you missed. Some people they don't check it if you like. So evaluate f the function at those critical values that are inside your interval, inside your domain, that are inside. Okay, inside the interval of A, comma, B. If they are outside, ignore it because nothing to do with the domain of your function. And there are going to be possibilities. Okay, so this is one source. The other source is you find the value of the function at the endpoint. You may get it because when you differentiate, remember when you differentiate, we ignore A and B. So you are going to find the f of A, the value of f of A, plug in, and f of B. That's it. Now we get a bunch of numbers, compare them together. So you're going to compare everything you got over here. The largest value is absolute maximum, the smallest value, absolute minimum. That's it. Compare. Okay, compare the values that you obtain. Okay, obtained values obtained in those parts, in parts 2 and 3. You compare them together. The largest value is the maximum, the smallest value is the minimum. So the largest, okay, the largest of those values, is the absolute maximum, and the smallest value, is the absolute minimum, absolute minimum. And it's always possible, according to this. No test is needed. We are going to learn a couple of tests later, but this is for the absolute max, absolute mean. We're just using the Fermat, the Cauchy theorem, and we don't need those. Okay, any question? So that would be your instruction for the absolute max, absolute mean, and at least be done with the first problem. So we have to check it. There are a couple of cases, but we usually give you one right away, straightforward. And for this next test and on the final. So let's check. So I would like you to find, give a couple of them, find the absolute extrema. Find the absolute extrema of the function on the given interval. Okay. Of course, on the given closed interval. Given the interval must be closed interval. For the open, you have to wait. First one, of course, a polynomial. Most of the time are polynomial types, but it would be popular in application problem in future. We are going to use it. So let's check this one. That's it. Okay, so you remind yourself that the domain of the function in this problem is this one. We know that the polynomials are defined everywhere, but remember, you focus on this domain only. So that's why you remind yourself. Are you ready? So solution. Remind yourself that you have to restrict yourself to this domain. This is going to be your domain. Step 1. The function is nicely differentiable, so to find the critical values only this case. So you are going to, solve f prime x equal to the 0 to get your critical values. Just remind yourself. Differentiate it, easy to differentiate, but be careful, f prime. So you differentiate it, that give it 3x squared. Okay, 3x squared minus 12. It's going to be an f prime. You did it equal to the 0. carefully solve for x. You know, this is going to be 3x squared equal to 12. So we get x squared equal to 4. So your x would be positive -2. Okay, so your critical values are going to be a -2 and +2. You know that you don't have any of those type 2 one. So that would be your first step, if you like. But quickly check to see if you are going to have them all together. Okay, check. Check with your domain. You see, what is your domain? Domain is -3 and 1. You just have a look and check, but this is the first one I explained it for you. You check, you find out you have a -2. -2, of course, it is inside. So x equal to the -2 is in D, is inside D. So you accept it. And you have x equal to the other one, x is equal to 1. X equal to 2. But x equal to 2 is not. Okay, is not inside. It's not in D. It's not in your domain, so you reject it. So the test is completed. So what's going to be the critical values that are going to take for this problem? The critical value that you're going to take for this problem going to be only -2. Okay, this is the place that you make sure that you don't miss it. If you miss this one and you bring both numbers, okay, then your final conclusion may be wrong, because you are not going to consider the f of 2 in your collection when you want to compare them together. You see, when we get to this last part, just compare, you know, the valid values that you're going to have. Okay, so check this one. Even if you don't, we don't usually write this. As soon as we have it, you see, we have a look, we say, oh, this is it. So I cannot have the 2. So you just simply drop the 2. You see, you drop the 2 and you say that the critical value is -2 and we accept it and you continue. Okay, so just check it, even if you don't write down. So we are done with the first part. Any question? So now we know the rest. The rest is you are going to find the value of the function at -2 at the end point of the interval, -3 and 1. Usually make a chart. Okay, so this is it. So as soon as you identify those valid, the numbers that we're going to have, this is the way you write it down. Make a chart. This is it. This is your chart. This is going to be your x values. And your function f of x equal to the x cubed minus 12x. Now the numbers that we're going to use, the number that we got from critical value is a -2. And the end point of the interval, -3 and 1, nothing else. Okay, the end point of the interval is going to be used all the time, but critical values, the valid one. Any question? Drop into the function and get those numbers. Okay, this is it. It's going to be -2 cubed. -2 cubed minus 12 times the -2. So that gives a -8 plus 24. Okay, that make it to the 16. 16 is one of the candidate value. Okay, continue, check the others. So that would be -3 cubed. Okay, and that's a -3 cubed minus 12 times -3. -3 cubed would be -27. That gives you positive 36. So the next number, the value is 9. That's the next candidate. Okay, we check the 1. That's easy. 1 minus 12. That gives us a -11. That's it. You compare these numbers together. The smallest one is the absolute minimum. The largest one is the maximum. As you can see, the smallest one is a -11. So we write minimum of f of x equal to the -11. That's a minimum. The largest value is 16. Maximum value of the function is 16. And you're done. You see, this means the range of your function, you see, if you like, the range of your function is going to be between -11 and 16. If somebody say, how are we going to get it? We say we get it at x equal to 1. So we don't usually write, you see, when you talk about max and mean, the value. So 1 and -11 is a minimum point. 1 and -11 is minimum point, and over here, -2 and 16 is going to be the maximum point. As we talk about it, you may say this maximum and the minimum at various places, different numbers. That's why we focus on the maximum value and the minimum value only. And they are going to be unique all the time. There's going to be only one number. Any question? So since it's a closed interval, remember, you must get it. There's going to be one. And if you miss, if you bring the +2 here, for example, then you compare it with the value of f of 2, so your answer may be different, which is not correct. Any question?
I have a question.
Yes.
If we write the answer as like minimum as the points, that's still fine and correct, right?
Yes, but it's not,
okay.
But it's not common.
Right.
Yes.
Okay.
Yeah. When you say minimum, you should give us value. And that's one of it. Yeah, but it's not wrong. It's not wrong. That's going to be the minimum point and the, that's going to be the case. Since it's a unique, you see, we write the value and we don't list the points, but it's correct. Just, Okay, that's
thanks.
case one. Okay, any question? That's case one. Of course, the popular case is you have to check. This is a polynomial type. So you may be given a trigonometric type. Okay, let's check what with the trigonometric. You see those 5 functions that I gave you as critical values? This is going to be, those are going to be our source of functions. So when we discuss a theorem, we bring those back again. That's why I wanted to check them, make sure you remember them. So that's why the next example is this one. So you get one of them on the test, maybe polynomial, maybe trigonometric one like this. This is like the one that you got on your previous, on the test. I think we give a course. Yeah, we give a sign. That was the same one. But I make it 4 and 2, which is the same thing. So let's see. So there is a point about writing the solution of this that I don't want you to lose it. So this is going to be our function. Of course, they restricted into the x and the 2 pi. Same thing. You want to find the, okay. We want to find these numbers. Okay, there's again, absolute max, absolute mean. So we start with the domain first, solution. Remind ourselves that you have to restrict yourself to the given domain. So domain is going to be 0 and 2 pi. The function is nicely differentiable, so critical values are coming only from the first categories. So you have to solve this equation only. You're not going to check that f prime of x does not exist for this one. Okay, so this is going to be the case. Nicely or carefully differentiated. F prime of x equal to lift of x is 1, lift of a sine cosine is going to be plus 2 cosine. Okay, that's it. Let it equal to the 0. So let it equal to the 0. Carefully solve 2 cosine x equal to the -1. So the cosine x would be -1/2, and make sure that you get it correct. And so a couple of you missed it on the test. Just go back and check your unit circle again. So there you are. You get it from the unit circle, but you can identify it where it is, where are going to be, so we can find it quickly. Remember, this is the cosine. So what we have a negative cosine. So the cosine is negative here, so one of them must be here, and the other one must be here. So we go to the table and we can find it right away. And this is going to be the leftover of the 1/2. 1/2 is cosine of a 60, so this is going to be 120, as you did on the test. So this is a 2 pi third on the table, and this is of course 180 and 60, which is going to be 240, which is going to be 4 pi third. Again, carefully your table, check your table. So the solutions are going to be x is equal to the 2 pi third and x equal to the 4 pi tilde. And double check it, make sure you don't miss it. So this is the case. Any question? Check unit circuit, make sure you get it right. So the critical values are going to be, critical values are going to be 2 pi third and the 4 pi third. Okay, that's a one. So you just have a look at it and you check it for yourself. You don't have to write it down, just to remind you. You check your interval is 0 and 2 pi and both of them are inside. So checking is completed. So I'm going to use these two numbers. Any question? So what's going to be next step? The numbers that we're going to put in the chart. We have two numbers for the critical values and 0 and 2 pi, the end point of the interval. Okay, so get your chart and you need to use your calculator for this one. So this is going to be the chart. So this is the number x and the function is f of x is equal to the x plus 2 sine x. The numbers that are going to bring here are going to be the critical values, 2 pi third. So that's a 2 pi third. Then I have the 4 pi third. And the numbers from the endpoint of the intervals are going to be 0 and 2 pi. So drop it back into the function to take care of it. Carefully, 2 pi third. So that gives you 2 pi third plus 2 sine of the 2 pi third. You go to the unit circle or directly your calculator. We accept both of them because we need the numbers. We don't accept it if you write it down in radical form or in terms of the pi. The numbers, exact numbers. So it's going to be 2 pi third. If you want to do it 2 times, the sine of the 2 pi third is positive and it's going to be radical 3/2. 2 times radical 3/2. These two would cancel out. So that gives you 2 pi third plus radical 3. Whether, use your calculator right at the beginning, but if you haven't, but you have to do this one for us, we don't accept it. Okay, so use your calculator, double check it, but I have 3.38. So this is going to be the first value. Any question? So you lose point if you write this one. Okay, because this has been the maximum. Minimum would like to be able to compare them together. Okay, so we need an estimate. Okay, ready? Repeat it. The other one, 4 pi third. Same thing. I drop the 4 pi third into the function, so that gives me 4 pi third plus 2 sine of the 4 pi third is equal to the 4 pi third. 4 pi third is here. The sign is negative, so you get only negative sign here. Okay, minus. But I explain it, so it's going to be a positive 2. It's a negative radical 3/2. So that gives you 4 pi third minus root 3. Again, we need your calculator. Double check it, make sure you arrive at this number. Yeah, I have 2.45. So this is going to be the second value. Okay. And for the next one is 0. That would be 0. It's a substitute that gives 0. 0 plus 2 sine of the 0. You know that the sine of the 0 is 0. So that gives me 0 plus 0, which is equal to the 0. So the next number is 0. And the last number is 2 pi. Check the 2 pi here. So that gives me 2 pi plus 2 sine of the 2 pi. Again, from the table, sine of the 2 pi is 0. So that gives you, again, we get 2 pi plus 0. 2 pi plus 0, which is going to be 2 pi. And the 2 pi is going to pi is 3.14. So that gives you 6.28. So this is it. So we have all the possibilities. We compare them together. Minimum. Okay, you compare them together. The minimum value is 0. So that gives you 0, the minimum. And you check the maximum. The maximum value, of course, is 628. So we get the minimum at the 0 and the maximum over there, and then you're done. Okay, and you know that you can graph it to get these two numbers, but we need algebra to get rid, and you have to give us all these details on the test. Okay, any question? So this is just to remind you that be prepared. Be prepared. You may have to apply it for the. Okay, you may have to apply it for this type of functions. Okay. Now, there is another group. Okay, another type that you are going to have in your book. This is the next example is crucial. Anytime you go through this chapter in your book or in any calculus book, you're going to see one with the radicals. Okay, and that would be the red flag, if you like. Pay more attention to it. It's not bad. But when you want to find critical points, you see in these numbers, those critical values are coming only from the type 1, horizontal tangent line type. We didn't have any those sharp corners one. So sharp corner ones would be provided by the radicals. So I'm going to give you this next example. In fact, I just want to emphasize that this example is in your book. Okay, it's one of the problem in your book that I want to do it because I want to make sure that you know it. And it's in any calculus book. There is a variety of this problem. All of them are almost the same. Let's see what is special about this example. If you want to check it, I think this must be number 23. Depend on which edition are going to have our Larson book, but it's in any calculus book. But it must be this number. So check it. If you see another one similar to this, just try it. But there are very few. Okay, so what's the problem? The problem asks you to find the absolute extrema. Find the absolute. Find the absolute extrema of this function. The function is f of x equal to, that's a function, 3x to the 2/3, okay, minus 2x. This is the one, but you want it, of course, on the closed interval of -1 and 1. Okay, let's see what's special about this group. That's a 2/3 in one other book, or they give you 1/5, 1/5, 2/5, 3/5. These are all of these categories. Okay, as soon as you see 2/3, this means pay attention, especially to the first part. So the domain is, we have to restrict ourselves to this domain. So the solution is, remind ourselves that we have to restrict into the domain of closed interval of -1 and 1. If you want to find the actual domain, okay, just remind you that this function is, we have to change it. It's going to be 3 cube roots of x squared minus 2x. But we prefer to stay with this one. You know that over here the index is odd. So the actual domain of this function is all real numbers because of the index is odd and this is x squared. But we stay with the given domain. Any question? So that's first part, that you have to stay with the domain, the given one. Because if you stay with this one, the domain is all real numbers, so you may not get the absolute maximum, absolute minimum. You get the relative. But they closed it so that we're able to find the maximum. But when you close it, according to the Cauchy theorem, there is 100% guarantee and 100% guarantee that you get the maximum. So that's a difference. Okay, so it's going to be the case. You have to find critical values. Oh, we see this is a radical one, so we may get it from different sources. So the sources are going to be f prime of x equal to 0. So you may get it from this, okay, or you may get it from this one. F prime of x does not exist. So you have to check both of them in the case of the radical function. Okay, and automatically you will see it in the course of the solving it. So let's differentiate. To differentiate, of course, we stay with this function because that's even if it's going to be in the radical form, we switch it. So just remind you that we stay with this function and we carefully differentiate it. Okay, so let's find the derivative of the function. So what is going to be your f prime? Exponent times coefficient, just the power rule. So I write it down, I simplify, it's going to be 3 times 2/3, x to the 1 down, 2/3 minus 1, negative 1/3. And derivative of the leftover would be just -2. So we simplified if we can, these two would be simplified. So we are going to end up with 2x to the negative 1/3. Okay, minus 2. So this is going to be our f prime. So I rewrite it, f prime of x is going to be 2x to the negative 1/3 minus 2. Again, we continue rewriting. Make it nice. So it's going to be 2 over x to a third minus 2. Continue, change this one into the radical. It's going to be 2 over cube root of x minus 2. Because you should be comfortable to handle it. So that's the best form that we have. So we get f prime of x equal to 2 over cube root of x minus 2. This is going to be f prime that we are going to use for the rest of the problem. Any question? Check this first. Let it to be equal to the 0. Then this would mean, now we check this one later because we have to check this. So the case one that we're going to check is to see where f prime x equal to the 0. So we have to solve this equation, 2 over cube root of x, okay, minus 2 equal to the 0. You have to solve this equation. You see, this is a kind of rational equation. So you have to get rid of the denominator. So you can multiply both sides by cube root of x, or that's easy. It's a 2 term, so just move the 2 to the other side. Okay, that's going to be the 1. We're going to use this type of techniques quite a lot. So it's like 2 over 1. Now cross multiply. Cross multiply. So if you cross multiply, so you get a 2 cube root of x equal to the 2 times 1, which is equal to 2. Okay, this is the way I do it. Again, the other option is multiplying by both sides by cube root of x to get rid of the denominator, you arrive at the same thing. Now you have to isolate the radical. No, it's a very mini radical equation. And when we want to solve radical equation, we isolate the radical cube root. So in this case, you can divide by 2. So that gives you cube root of x equal to 1. And then you know that you have to get rid of the radical term. So what we do, we raise both sides of the equation to the power of the radical expression. The power is 3. So raise it to the 3rd power. So that gives you cubed. And that would be cubed. Now we lose the radical. So that gives us x equal to 1. Okay, so cube root of x is going to be x. So that gives you x equal to. Okay, so x equal to 1 so far is a critical value. X equal to 1 is a critical value. Any question? But most of the people, they missed it because they stop here. Remember, it's a radical function, so you have to check the possibility of the second group. Sharp corners. So you check to see if this is going to be the possibility, the sharp corner one. Are we going to get anything from this one? Is there any place that the f prime does not exist? The same thing. Come back and check. We get this cube root of x down the denominator. Okay, down the denominator, and you know that this function f prime is going to be undefined when the denominator is equal to the 0. So check for what value of x this denominator would be 0. Any suggestion? If you plug which number for x, the denominator will be 0 here. Number?
0.
0. Excellent. 0. So it's f prime of 0. Remember, you let it equal to the 0. You see, if you have difficulty to find it. Denominator equal to 0, that give x equal to the 0. So you explain that, oh, f prime of 0 does not exist. This is where you get the short, you get the vertical tangent line. And you have to check to see if 0 is in the domain, because they restrict the domain for you. Yes, 0 is here. So f prime of 0 does not exist, and x equal to the 0 is inside the domain, in the domain D. So this is a critical value. This is where we get the vertical tangent line. Okay, that's why it does not exist. Okay, so x equal to the 0 is also a critical value. Okay, so you got to be careful about the second possibility that you're going to have. So what's the conclusion? The conclusion is going to be you have two critical values. So therefore, there you are. Critical values of your function are going to be 0 and 1. That's make it, special about this function. Any question? So make sure don't miss the second part. And the first part, a little bit of algebra. You have one in your practice test that I'm going to post it for the coming, our test number 2. There's another one. It's very close to this one, but the algebra is a little bit more, but not bad. So check it. So this is the part 1. Of course, we are not done. So the checking, the checking are going to be completed if you like, we already checked both of them. But the checking that both of them are going to be inside the domain, yes. 0 is inside, we talk about it, and 1 is, it's closed interval, it doesn't matter. So checking is completed. So this means you are going to get a chart, find the value of the function as 0 and 1, the critical values, and endpoint of the interval. Endpoint of the interval are going to be -1 and 1. You already got the 1 here. Okay, so we go to the chart and getting and comparing the values together. Okay, you need that chart to be able to take care of it. Okay, this is it. This is going to be your chart. Your chart form the x here, and the f of x is going to be your function. Okay, you better write it down in that format. It doesn't matter. Okay, in the radical form would be better. You can use your calculator, of course, to find this part. So this is your function. Okay, and the values that you're going to check for the critical values, of course, we have 0 and 1. And the interval is -1 and 1. You already got the 1, so the -1. Any question? So we get the 0 and 1 from the critical point parts, okay? And then we have the endpoint of the substitute. If you put the 0, of course, we get 0 because everything is 0. So that gives you 0. Okay, that's going to be the 0. And then if you put x equal to 1, so that would be, okay, it's going to be 3 times, it's just, it's cube root of 1 minus 2 times 1. 1 would be 1. So that gives you 3 minus 2 to get these numbers. Okay, so that gives simply 3 minus 2, which is equal to 1. So this is one value, and this is going to be another value. And if we put the -1 here, so that gives you 3 cube root of -1 squared. Okay, minus 2 times -1. And -1 squared is 1. So that gives you 3 cube root of 1 and negative positive, they're going to positive 2. So the cube root of 1 is 1. So it's going to be 3 times 1. Again, you can use your calculator, okay? It's going to be 3 times 1 plus 2. It's basically 3 plus 2 equal to 5. That's it. Any question? So we have the numbers to compare. It's going to be 0, 1, and 3. So the minimum value of the function is 0, and the maximum value of the function is going to be 5. So that gives you the final answer. Okay, so be careful about this You get a couple of them because it can happen, in other part of the that we go on, but just theorem of algebra, make sure you are familiar with this type of ideas. That's it. We have the absolute and absolute maximum and the absolute minimum of this function. Any question? So we're done with the section, okay, 3.1, very dense section. So at the end of this section, what we did, we introduced our target, okay, those relative maximum, relative minimum. And the question is going to be how we're going to find it. By the Fermat theorem, there are two places that we're going to find when the tangent is going to be horizontal or the tangent is going to be vertical. But we took care of the problem of the absolute max and absolute min so far, meaning the largest value and the smallest value. The next target is going to be relative maximum, relative minimum. Remember, the maximum minimum at the a special type. That would be different story. Okay, you can do this one right away, but the other one, we have to wait to get it. We do it. I'm not going to do that one today because it's going to be the section. We have to pause if you like in order to talk about it. So what we do is first we pause in section 3.2. We look into the property of these critical values. We check to see, again, we want to find sources. But before getting the sources, we show you that they are useful and they are going to be around, okay? Because, the absolute max, absolute min was straightforward. So you are going to see two great theorems of calculus. And basically, one of them really, we call it the mean value theorem and the roots theorem. So two theorems that we're going to discuss. This is one of them, the Rolle's theorem. Some people in calculus, they ignore it because you can ignore it. This is good for the algebra. But the next one is mean value theorem. Mean value theorem. That's a great theorem in mathematics. We call it midwife of calculus. If you want to do anything special in mathematics, you have to go through this one. So in 3.1, we are going to investigate these two first, then we come back in 3.2 and start talking about it. So probably, because there is no lecture tomorrow, okay, probably we may have to give you your test by the end of this section only, 3.2, okay? So I'm going to discuss the 3.2 at, when you're coming back on Wednesday. Then we practice for the test and we give you your second test. Then we come back to the 3.3 and then we talk about the relative maximum, relative minimum. Then we finish it. So that's going to be the roadmap. So study this one carefully and make sure I let you go submit your quiz and no class tomorrow. And we come back and we take care of this great section 3.2. These theorems are going to be important in calculus. We cannot ignore it. In some books, they just give you the statement of the theorem and ignore it, but we can't do that. So we go over it. And that's it for today. Any question? So make sure you submit your quiz on time and your assignment. And I repeat it again. If you have any question on your quiz, on your test, you just email me before 5, okay, 5 to 6. Then you can join on Zoom. I bring your paper. You can have a look, and if there is going to be anything, I can explain it to you. That's it. Have a good one and happy 4th of July. No class tomorrow, remember. We come back on Wednesday. Bye-bye. Have a good day. Bye-bye. Thank you. Thank you.